from the Polytechnic University of Madrid in 1982. In 1986, he became PhD in civil engineering. In 1996, he became a Bachelor in Science in Economics. He's full professor of Building and Precasting Department of the School of Civil Engineering of the Polytechnical University of Madrid. He's the director of the laboratory of the Institute of Technical Materials and Constructions, INTEMAC, member of the FIV and ACI, American Concrete Institute, member of the FIC Commission on Prefabrication, member of the Administrative Council of a Spanish branch of FIF, director of 9 doctoral theses, author of over 100 articles and Congress presentations, and co-author of 24 books of constructions. Jaime, you have the word. Thank you.
Sorry, and thank you, Mr. Chairman. Let me start by saying that I am very glad to be here because the organizers are good friends of mine. We've known each other for many years, and I am very happy with this invitation. Okay, I'm going to present the subject, design quality control, key points. Obviously speaking about building construction, but first of all I need to introduce my company because the subject arises mainly from the work done by my company, INTEMAC. All of you know by now Professor Calavera, who is our founder and our honorary president, who gave us an interesting lecture about tall buildings. And INTEMAC has been working on quality control of design and construction since 1967, both on public works and building construction. I would say that perhaps 40% of our work was done in building construction, and both in projects and design and on-site construction. And as we are going to see, nearly 50% of the pathologies in buildings arise from the design. I'm going to show you later figures taken from a book written by Professor Calavera, and we will see that the design is the most important source of problems. In Spain, quality control has never been mandatory, but since the approval of the building law in 2000, the companies, the insurance companies, normally require some kind of quality control of design to give the 10-year insurance policy. And also we have here for concrete structures some regulations included in our Spanish code for concrete structures. This is one of the charts I am going to show you, taken from the book written by Professor Calavera. And we can see that the cause of the pathological problems in construction, in buildings, come from design. This is an average value, but perhaps between 40 and 50%. 42% is the mean value of the inquiries included in the book. Construction could be almost 30%, materials almost 15%, and utilization almost 10%, and miscellaneous the rest. I know that this is quite hard to see this chart, because if you're a designer or an architect or an engineer, it is very hard to see that you are the cause of the problem. But it's obvious that the chart is true, because in all activities in the human life is the same. I think the more the human intervention is, the more problems we find. That is the same for traffic accidents or for other activities. And design, the most human intervention is in design, and the second is in construction. And that gives an idea of where the human intervention is, not who is the bad guy or the good guy. No? But it leads us to control the design, because evidently the design is the principal source of problems. Also taking into account the part of the building, nearly 90% of the problems arise from structures and foundations, facades and roofs, and interior walls. I am going to speak about these three topics, not building systems. That is not my specialty, and there are a few cases in building systems, installations, because they are more industrial systems than construction systems and are more regulated. And also, if we see the cause of the problem due to design, separated in 4 topics. Perhaps we can think that the calculation mistakes is the most important part, but we can see that it is not. The detailing is the most important, and either for omission, not to include the good detailing in the design, and also for include wrong details, no? And we can see that detailing is the most important cause of problems due to design. Well, I have selected these key points for structural elements. I have selected 6 topics with examples because they are the main source of problems in quality control of design. Lack of calculations, conceptual mistakes, load actions, dimensioning with 2 specific references to share the interface between concrete cast at different times, and deflections. That was an important source of problems here in Spain. In this case, dimensioning is in some relation with imprecision of standards and also detailing. As I told you before, that is the main source of problems. And speaking about other parts of the building, I'm going to speak about facades and roofs. Okay, lack of calculations. It might seem improbable, but how to design something without calculation, but sometimes happens. Mainly due to these reasons I have put here. Overconfidence of the designer. In some cases, we think that we know how to solve the problem and we do not use the appropriate calculations. Also, the use of solutions that have given a good result in the past, and we extend the solution. That is very common in some cases about geotechnical reports, as I am going to say. Also, lack of time. That is one of the problems, and also because we don't know very well the calculation procedure and we omit it. For example, as an example of lack of calculations and in relation with overconfidence of the designer, this is a quite general example, the lack of geotechnical report. For example, this is a case, a fairground in Spain, Parque de Atracciones, which obviously had its own geotechnical report, but the lot was very, very large, and they extended the solutions of foundations for other parts of the construction, like this one, in which the soil was not the same. And that led to the problem on foundations, as we can see here in the calculation we did. With the defects we can also see in the pictures, due to extend the solution of foundations to other parts of the construction that were not covered very well by the geotechnical report. Also, in the problems due to detailing, I think these problems can have 2 causes. They could be caused either by omission of the necessary detail or because the included detail provided a bad solution. 2 things quite important are that standards and also computers do not consider the detailing as well as calculations. We have standards that normally cover all the procedures we use, but we don't have a large catalog of detailing also covering the specific details for any solution we can use. And as some advice, I would say that in some cases it's a good thing to include or to draw the specific detail at real scale, because that gives us the impression, and we can see, for example, in some cases, the impossibility to make it, as I am going to show now. For example, this is a car park that collapsed in Spain, and the cause of the collapse was the punching. And we can see here that the detail drawn, or the detail more or less thought, is the one shown here. But if we take into account that the slab is 180 millimeter depth, if we consider 25 millimeter cover, and we consider 16 millimeter bar at the top and 12 millimeter bar at the bottom, we see that we only have 74 millimeters for all the shape of the bar, including the bending, and that means that this bar is horizontal and with no effect for punching. That was the cause of the problem. Also, wrong details or not included detail, for example, the bendings against the cover, like in this case, that we know that this is the correct detail, and some cracks in this case and some collapse due to this bad detail. And conceptual mistakes, what I understand by conceptual mistakes? I understand by conceptual mistakes things like more or less philosophical things that are completely forgotten in the project. For example, this is or tries to be a drawing of a building with 3 levels under the ground. Normally we build us with diaphragm walls, and we consider the slabs as a support for the diaphragm walls. But we normally do not consider the effect of the diaphragm walls in the structure because the slabs are continuous and we don't have a special effect. But in this case, we have a gap in the structure, and the effect of the diaphragm walls needed to be considered, and it wasn't. And we can see here the problems derived from to forget this calculation. Also, in conceptual or load evaluation mistakes, one example quite common is to convert concentrated loads to distributed loads. That happens mainly in areas near buildings or car parks or things like that, in which we use distributed loads as concentrated loads, because we have a vehicle traffic, and in some cases could be reasonable, but in some cases it is not, like in this one, because we can see here the calculations, and the shear was unacceptable in some nerves, as we can see the defects at the bottom, in the pictures at the bottom. Also, as load evaluation, examples of inadequate modelization, quite common in prefabrication, for example, the real situation of a column, and the model adopted that in some cases do not include the moments due to the corbels, and that leads us to a problem of moment in one of the sides of the column, like in this case. And as examples of dimensioning, in some cases in relation with imprecisions of standards, I'm going to speak about one of them, shear at the interface of concrete cast at different times, as all of we know that happens in this kind of sections, composed sections, with a prefabricated member and concrete cast in situ. And in some cases, the situation is quite hard, because we do not have enough surface to resist the shear, and the standards were not didn't consider very well this effect in the past. And I think now, today, also the Eurocode has some lacks and some things quite wrong, but the systems have changed, and the problem is less now than it was previously. We can see here also a load test conducted in a structure which was under consideration due to the shear, and the structure collapsed during the test. And also deflections, as dimensioning. All of we know that large deflections, mainly not related to safety problems. There can be a safety problem added, but without safety problems, deflections can cause damage to non-structural elements, mainly interior walls and facades in some cases, or pavements. And these problems was very, very important and very great in the 60s in Spain. And fortunately, it has decreased, but it has increased due to the reasons I am showing here, but now it has decreased because we have changed the standards. It has increased in the past. 10 years ago, it was probably the most problem in construction, due to the increase in span length, also the use of high-quality steel, modern design techniques, and the use of different structural systems. Mainly the two I show here. we used in the past deep beams, and now we use a lot flat beams with the same depth than the slab. And that gives the problem that we need to add both deflections, the deflection of the beam and the deflection of the slab, to consider the limiting deflection that are considered by the codes. Here we have normally the three ways that codes consider for control of deflections, more than control of deflection, to control or to avoid the damage due to deflections. The first one is limiting the slender of the slab in relation with the span length, and also limiting the active deflection or the total deflection. The active deflection is the deflection that takes part after the construction of the building. Here we have the limitations given by the Spanish regulations. And common mistakes calculating deflections. I would say these four. The first one, to omit the calculations, that was quite common in the past. Also the use of an inappropriate modulus of elasticity that is completely direct with the deflections. Also not to consider the cracked section for concrete reinforced sections. This leads to the use of an inappropriate moment of inertia. All of us know that the cracked section in concrete reinforced structures could have 1/3 of the moment of inertia of the cross section, and also to neglect the construction process, the use of different levels of striking material. The pattern of damage caused by deflections is like it is shown here, with inclined cracks and also with vertical and horizontal cracks. And one thing that is quite common in this damage is that the damage is more important in the lower levels than in the upper levels, due mainly to the transmission of loads through the interior walls. Here we can see some inclined cracks and also cracks in cantilevers, as also buckling in an interior wall. Okay, let's change gears and move on to speak to another part of the building. Speaking about facades, I would say that one of the main problems, one of mortal sins, is the lack of joints or the distance between joints. We need to consider joints in facades in order to avoid the thermal effects. In Spain, we have this chart with the maximum temperature in the air, and it gives us temperatures about 52 degrees in some parts of Spain, not in Santander, obviously, but we need to increase the temperature due to the solar irradiation, and that means that perhaps we need to consider 70, 80 degrees in summer and -12 in winter. This, we can see here a measurement made by us, and this is a real measurement, almost 69 degrees in a facade. Also, other problems of facades concerning with stability. We use a lot here the two-wall system facade, brick mainly, with one interior wall and other exterior wall and air chamber or insulation between them. And the exterior wall needs a support more than 2/3 of the depth of the wall. If the tolerances of the facade, the structure in the facade, didn't allow us to do that, we need to consider special details for supporting the facade, like in this case we can see here with a metallic structure to maintain vertical and well supported the exterior wall, because if not, we can have these problems, the lack of support in this exterior wall, and also the collapse in the other parts. We can see here that the exterior wall passes through the beam without touching it. And also details about draining system of the air chamber. This is a specific or general detail in which we put waterproofing membrane with draining points, each 1.5 meters. But, for example, in some cases, the specific detail is not applicable, like in this one, because we have some ornamental pieces. And as we can see here, not to consider the specific detail in the design and to use normal details can lead us to this situation, because they put the draining points in an upper level than the waterproofing membrane was. And that caused humidities and damages logically in the level of the waterproofing membrane. Also in facades, we need to consider the effects of the wind that are not well considered in the standards, because the standards normally consider the wind for calculations of structures, and not for facades, mainly for curtain walls and ventilated facades. All of us know that wind is a statistical variable. Wind has gusts of wind, ráfagas de viento, and that means that the wind has a density function as a statistical variable, normally represented by the pressure coefficient that we can see here. That means that we can use uniform pressures or uniform suctions for large areas or to calculate the structures, but in small areas like windows or like small pieces of anchorage, we need to consider peak values. These are not very well considered by the standards. And also the buildings have their own shapes, and the standards only consider square and some logically shapes, but we have a lot of shapes in buildings, and if we conduct a simulation, or we conduct a wind tunnel test, we can see that depending on the shape of the building, we can have a lot of peaks of suction that are impossible to consider by the standards. For example, we know that inclined roofs, like this one, have in some places suction, whereas all the roof is mainly in pressure. And we can see here how the popular culture has adopted solutions to weight the roof in this part to avoid the suction of the wind. And that is the problem when we have some difficult shapes, like the one on the left, and also some collapses, general collapses on the other case, because the effect on this corner and in these places could be greater than thought. A railway station in Spain that the roof, the flat roof, the English name is Canavy, collapsed due to the wind in suction. This is a railway in the northern part of Spain, not Santander, not in Cantabria, fortunately. And also we can see here that the same problem, but with an illustration that we normally consider the effect less important in the lower levels than in the upper levels, and as we can see here in the figure that is on the right. But in some cases, we appreciate that the defects are spread out all over the building, and that means that they are peak effects depending on the shape of the building, and we need to consider them in some cases, mainly in tall buildings when we use curtain walls more effectively. Finally, I'm going to speak about roofs. How much time do I have left? 8 minutes. Okay, perfect. I'm going to speak about roofs. In my opinion, design of a roof must include these 4 points: joints, slopes, holes, and the appropriate details for everything, because if not, we can have problems, as I'm going to show. We need to define the slopes, the draining points with appropriate details for everything. For example, the bad definition of slopes could cause the pooling of water, as we can see here with the derived problems of waterproofing. And also, inadequate slopes could cause these problems that Americans call ponding, and I am going to illustrate the problem. If we have a flat roof with various slender planks, because we normally do not consider a large load, and we have a heavy rain. The process is like this. We pull water, the water increases the deflection causes that more water is pulled, and finally we can have the collapse of the structure. As in this case, for example, this is a very flat roof. The draining points, as we can see here, had a gap, allowing some pulling of water. And also we can see the weather, quite alarming for raining. This is the pulling of water. And also the collapse, we can see the planks, very slender, and also in this part, the deformation caused by the water and the collapse, the resulting collapse. Also, one thing very important is the definition of holes, to consider all the holes and the draining points, because if not, we need to drill, and drilling always causes problems that are difficult to solve. For example, in this case, if we need to, I think this is one of the mortal sins of our construction, the use of drilling, because in some cases it's very difficult to waterproof the detail, like in this case. And the solution is to block the drain and to build another one, as we can see here. That we call in Spanish chapuza. I think in English the translation is cowboy job. I don't know why, but in some cases you hear that when someone does something wrong in your house, you say, "Hey, buddy, where did you let your horse?" That means something in relation with cowboys. And also bad definition of roofs, for example, in this case, not to know very well how a roof works, because in this case the pieces are not thought for this solution, because a ventilated roof needs the insulation in other place. We need to have the insulation with the cool side in the air, in the chamber, because in this situation the insulation is not effective. And mainly, and I am going to finish, the details of waterproofing. These are very important because we have a lot of systems of waterproofing, membranes, bituminous, plastic, two-layer system, one-layer system, and the welding of the membranes is different depending on the case. Also, we use liquid membranes, and in some cases we use standard details, like this one, and the detail is different if we use different systems. For example, the two-layer system need to solve this detail, as we can see here, passing the layers alternatively one to other, because if we put the two layers together, we have, like in this case, the rupture in this part due to the adherences, no? And also the details for drains, because in some cases the detail is not appropriate. Well, it has the appropriate definition, like in this case, but with lack of details and the clamps and so on, with difficulties after that for solve it. And also a very important thing, mainly in industrial buildings and all buildings, the ducts that crosses the roof, because we need to consider the specific detail, because if not, the given solution in any case is to use polypropylene foam that has shrinkage, and it's quite difficult to waterproof the ducts. And the joints. If we consider, like in this part, a general detail, depending on the system, 2 layers, other system, we need to consider also the finishing and protection, the dimensions and the specific detail, because in some cases the 2-layer system need layers to separate the mastic in order to avoid adherences, because if not, the waterproofing breaks in this point. We need the specific details, like these ones, because if not, this is the problem of the joints in many cases, in which we have a leak of water. And in some cases, the solution, the repair is very difficult, because the access from above is quite hard, because could be urban space or places in which we have no access. And the cowboy job in this case is to hide the problem, not to solve it, using chase to take out the water, not to solve the problem, as we can see here, and also as we can see here. Put in chase to take out the water and not to solve the problem. Okay. I've almost finished. And thank you for your attention, and come back in the summer.
Thank you so much, Professor Fernández Gómez. Now it's time for a short break. So first of that, I would like to thank again to the institutions that have promoted this plenary session. So thanks to the Colegio de Ingenieros Industriales de Cantabria, the Colegio de Ingenieros Técnicos Industriales de Cantabria, the Spanish Institute of Simming and its Applications, and to the Institute of Materials and Construction in TEMAC. Well, at 11:20 we will start the parallel sessions in the different rooms. Thank you for your attention.